Hello, everybody. So today I will talk about a research project we have at Total Energies that bridge academia research and industrial research for wind energy mainly. So Total Energies is a multi-energy company, as you know. We have a big ambition, large ambition of 100 gigawatts of sustainable renewable energy for 2030s. And a big part of this ambition is in developments of wind farms. So we are acting as a developer. We are not manufacturer, but we will see that we are also interesting to understand what is behind the hood that is provided by the OEM, the provider of wind turbines. And certainly we will be more and more operator in the future. So we at the moment are developing a lot of very large projects of multi-gigawatt wind farms all around the world. And just to say an example, wind farm with 1 gigawatt of capacity is able to provide the electricity for 350,000 US homes equivalent. Why we are doing numerical simulation, and in particular we will see high fidelity simulation in this domain, because this is quite an old industry, because the wool industry has changed a lot in the last decades. For example, the wind farms are more and more bigger, with a lot of turbines inside the farm, with high density, in higher density area. For example, a prime example is Europe. You see on this map of Europe the wind farms in development and in production. So in orange, you have the farms in production, and you see in gray all the projects for the future in development. So it's completely crazy, if we can say. And so farms are near other farms and can interact together. And sure, we have a big offshore project, but there is also more and more projects in challenging, complex terrain onshore, and we are interested to understand better also for those kind of projects. On the other side, the turbines are also larger and larger. So from small turbines 20 years ago, we were already big, but 1 megawatt, 2 megawatts. We are more now, as a standard, 4 megawatt, even 5 megawatt onshore. The average power for offshore turbine is 10 megawatts, and new projects are developed with 15 megawatts, and even bigger turbines, 17, 20 megawatts, that are completely gigantic structure never made by human before. So you have a map on the right, a picture on the right that you use the scale of those gigantic turbines. So it raised a lot of big challenges and question to understand. So there is challenging about the supply chain, the connection to grid, because they are very powerful wind farm with a large capacity. But we will not talk about that today, but more on the focus on the resource on yield assessments, the design optimization, because as developer, we are mainly interested in this phase of the development, the design, the optimization of the layouts. So a lot of research projects and physics involved that are coupled together, fluid dynamics with aerodynamics, with the turbulence. One of the main effects to take into account is the wake effect. It means that one turbine can affect the turbines that are down flow, so behind other turbines, decreasing the wind speed. So in fact, this is the primary source of energy for the turbine, and increasing also the turbulence. So it means adding fatigues and loadings on the turbine. So this is the most aspect we want to understand. But there is also new aspect now we want to understand, like the blockage effect, the induction factor in front of the turbine, or at the scale of the farm. With very high density farm offshore, we have also deep array effects, interaction with the upper atmospheric boundary layer, also effect with lower jets. So a lot of effects to understand. And this is typically multi-scale in space and time. So you can want to perform, for example, on your picture on the right, simulation at mesoscales, spatial dimension. I mean, mesoscale is about 250, 300 kilometers squared, and with mesh size, the little mesh size, tens of hundreds of meters, 1 kilometer, to understand interaction between farms in proximity, or to have a better understanding of the inflow into the farm. And you can also go at downscale, at inside the farm. So here we are typically speaking about tens of kilometers with mesh size that can go up to 10 meters of resolutions. And even further, if you want to have blade resolve simulation just around the turbine with the centimetric mesh size and very, very small time step for a few physical time simulation of few seconds. But it's more on the manufacturer side. All those big challenges are described in a report already old, 2019, and updated in the Grand Challenge Revisited. So you have the link on this page if you are interested in. So just to have a picture of what is the model that is the main model used in the engineering design office that we use in the business. It's a very simplified model, analytical formula, to compute the yield of a future wind farm and also to optimize the design. So for this, you need some information. So you have information that are provided by the turbine manufacturer. For example, a power curve that gives you, according to a certain wind speed, the power production for a certain model of turbine. You need also historical data, meteorological data that are given by weather prediction and also measurement. But perhaps you will need also simulation to reassess, to recompute some data at the, for example, the height, the hub height of the turbine. Typically, those data are at 10 meters or higher altitudes. But if we want exactly at the hub height, 100 meters, for example, we need to recompute this with a CFD software. And sure, after you want to have a design of your farm with a layout, with a less possible interaction between turbine, and have the better cost of construction, the lower the capex, to optimize the levelized cost of energy. So with all those data, plus a model, very simplified model, called the original one was the Jensen model in the 70s. It's a very simple analytical formula where you have just a wind speed decrease behind the turbine with a cone expansion to a recovery. And you can add also higher fidelity, it's not high fidelity, engineering models with Gaussian models, or taking into account some effects like the yaw. The yaw means that you are not completely aligned with the wind, but you have you are yawing your turbine, so the wake is deflected, and it will not affect the turbines that are behind. Could be interesting in certain situations, but mainly those are analytical formula, not physics-based at all. So they have an advantage. They are very, very fast to compute, and so you are able to use them in an optimization loop, but the results are not very precise. So now with the development of the new farm, bigger, as I said, higher density, there is too much effects that are not taken into account, and we need to put that in those new models. We also need to calibrate those models, so we need data and simulation for that. This is why we want to have a higher fidelity stack of simulation to be able to field those engineering models. So this is why we want to invest in this area of high fidelity simulation workflows, but we can't do it alone. And so we partnership with the National Renewable Energy Laboratory for a long-term project to be able to develop a integrated stack of software and workflows inside Total Energies in partnership with NREL. And mainly we are focused on yield and resource estimation for very large wind farm and also in challenging complex terrain onshore. And all those simulations rely a lot on HPC, high performance computing simulation. This is why I speak about that today. And so to say that we are investing a lot on this project for now and the future. So we are working both for our internal R&D and also to develop pre-industrialized version or industrialized product for our business line. And to have a success, a key of the success of the project is to also have stack exchange. So I am now in Colorado to participate with the team at NREL for this research project, and on the other way, to have people from NREL working with us at Total Energies in the future. So we developed three workflows, three models. In this project, we have also other projects involving high fidelity simulation for wind energy in the company, but specifically with NREL, we want to develop those three workflows. So those workflows are runs on LES simulation to assess resource and yield on very large wind farms. So first we need geospatial information. Could be tricky, but it's a pre-processing step. And to have Reynolds average computation capability in complex terrain to feed the engineering models I presented you before. We also, for certain circumstances, to understand well the loadings on the turbine, if there is curtailment situations or really tricky dynamic effects that are not able to be known by engineering models, to have LES simulations. So the cost is much more important, but it's also important to have this for our project. And for very, very large wind farm, we are not able to do computations purely with LES and accurate models of the turbines. So we also invest in a tool called FastFarm, developed at NREL, quite of mid-fidelity range simulations. So for all of those studies, as you see, we have a lot of parameters. Mainly, the interest for the business is to have a knowledge of all the wind sectors. So we can divide in 18 or 36 wind sectors. We can be interested in one wind speed for all those sectors, the rated speed of the turbine, but we can also investigate other wind speeds, so below rated or that are above the rated speed of the turbine. And surely we want to investigate a lot of atmospheric stability condition, because usually in the R&D we use the neutral stability condition for the atmosphere, but this is really theoretical. And when you have stable or unstable situation, atmospheric stability, there is really, really different effect. So for example, for an unstable atmospheric condition, the wake propagation recovery is much faster because the turbulence mix much faster. And this is the contrary on very stable condition, where the mix doesn't occur rapidly, and so the wake propagates very, very far away. To give you an example, this wake can have an effect at the turbine level up to tens of kilometers, 5-6 kilometers. And you really see the effect on the turbine as 5-10 diameters. And now the turbine diameter could be much bigger than 200 meters. So you make the computation, 1 kilometer, 2 kilometers away, you have a big effect of the wake on the turbine. And at the farm scale, it was proven in Europe that the farm can interact with other farms up to 50 kilometers of distance. So it's quite large. So the core of the project for the first year was to develop the good software stack. And it's not so easy because we have different interests, so in the research and in the industry. And so we should limit the number of dependencies, but it's quite huge because we want to do, as I say, different scales in time and in space. We need different tools, but we want to reduce the number of tools for the deployment because it has a cost for us to deploy this on our own HPC. So the core tool here, it's a computational fluid dynamics software called AMR Wind, based on the IMRX workflow, kind of similar to COCOS for those who know. And this is block structure CFD software with capabilities to model the turbine with actuator disk, so simple model, or to couple with other software like the OpenFast multiphysics software, OpenFast is also another software developed at the National Renewable Energy Laboratory that couples aerodynamic, elasticity for the mast and the blades, the controller of the turbine, a very important part of the turbine, and couple this with the AMR wind flow simulation. We have also developed in Total Energy our own model for some reasons. OpenFast quite big, complex, a lot of features, and we want to have a simpler model for our R&D project. So we developed CRO for this purpose, and it is also coupled with AMR wind. And we work closely with NREL to have the two version compatibles. We need also other package for doing optimization of turbines from generic models to OEM. Wind industry is quite close industry in the sense that we don't share a lot of data. So for the manufacturer don't want to provide the specification of their turbine too much. It's difficult to have real SCADA data from the farm because we are new in the area. So we need to fit real turbines model to generic models that are developed in the academia. So to try to retrofit the model to have a better estimation of those models. We need also, for the mesoscale part, numerical weather prediction model. So we are not doing numerical prediction at Total Energy, but for the meso part, it means that for the scale of 200 kilometers squares, we need those softwares and to couple and downscale with the CFD. So we use WARF for the moment. That is the most used in the academy. And also we plan to go toward Earth, which is also developed as a new generation of software for NWP, numerical weather prediction model for wind industry, based also on AMRX. And we have also glue codes in Pythons and also engineering models that are in the loop, plus post-processing like ParaView. So what is important to understand, it's already a big collection of software. On top of that, there is a Hexawind manager that is based on SPAC to help us to install a well-known version of the software. And we also have a lot of Python dependencies. And it was not so easy. It's an important part of the project to agree with all those open source projects developed at NREL, or partly at NREL, to have a clear identified tag for all the versions of the software that work together for our own needs. And so now we are ready for that, so it's good. And we also want to limit the number of software used, and mainly also on the CFD part. So at the origin, we plan to use both the NALU Wind software and the AMR Wind software in the Hexawind project led by Mike Sprague. But we prefer to limit to only AMR Wind and perhaps to invest a little bit in the development of new features that we are missing in AMR Wind, the RANS capability and also the complex terrain capability. Concerning the deployment, so there is the Hexawind manager over SPAC, so it helps, but it not solves everything. And there is also for all the Python parts, we use CondaForge. I should say it's also a difficulty because in the academia, researchers are quite free. They want to develop a lot of things, use new packages all over the time. And at the end, when I try to install a unified version of the stack for all those software for the Python part, just had look at the dependencies. There were 700 packages of dependencies. So I remember when I was programming 20 or 30 years ago with only BLAS, C++, BLAS, and now we have 700 dependencies. It's a lot, and it's a nightmare, in fact, to maintain this. So we need to freeze a version because else we enter into a kind of a nightmare, a cycle of one of the project want to change a version that it clash with other versions, and it's very difficult for us because we need one uniform, long time support version, well validated for our industrialized product. And we need also to develop some tools, glue tools, to help reduce the difficulty to understand, for example, the input fight of AMR winds are very generic. We need specialists. We want to focus only on our specific workflows. So for that, we do that in 3 stages. So all the new developments are made, and the R&D are made in NREL, and the first simulation and validation, verification validation on the Kestrel cluster of NREL. So you have the specification on the right. And as soon as it is ready, we interact with the teams that are in charge of the HPC in Houston for the R&D at Total Energy. And so we integrate and deploy all those tools. So here we make perhaps some modification. We have interaction with the team of NREL. And when we are happy with the deployment, the next step is to deploy to the industrial cluster, so much more restriction on this cluster, Pangea 4 in Pau in France. And here it's much more difficult because this is a closed cluster. We have other consideration, for example, cyber security, so there is a lot of people involved to really deploy the stack. And we need this intermediate part at Houston that help us to put and transfer on Pau. So about the development, so we don't want to invest too much in the developments. So thanks to all the works that have been done by the past at NREL and other laboratory in open source, we are able to reuse all this stack. But we need to limit the number of software used to add additional features. So we developed the immersed boundary condition model for the complex terrain. It means that we are being able to detect with the topography the cells that are intersecting the topography. Cells behind are ghost cells, are blank cells that are not participating to the computation. Cells below are standard cells, and cells that are intersecting, we just add a forcing term to this in the equation, additional forcing term. And so it works very well in the first generation, but we need to improve also this model in the future. We also did it for this project to develop a RANS capability because AMR Wind at the origin is only large eddy simulation software. So we did it. And we also add RANS 1D simulation to initiate the computation to bypass the inflow computation that is needed for LES. And we also develop a simplified environment for the user. So to develop this and validate this, we need also a good use case. And in fact, we have chosen two use cases. One for the NREL side, called the W2 Bigelow Canyon. It's a kind of open source case, not too big, 50 kilometer squares, medium complexity in the topography. And the advantage of this case, there is a lot of SCADA data that are well known by NREL from the wind farms, and also a lot of historical meteorological data. And this is very well studied by NREL and other researchers in the academia. So we are confident when we have results on this that we know what we are doing. But we want also, for this project, a more challenging case. So this is why we use an internal case at Total Energy called La Réunion Island. It's 100 kilometers square with very high complexity in the topography. We have one farm in production, and we have the SCADA data and historical meteorological data on it, and it's well studied by Total Energies. So I will present shortly few results, preliminary results, that are running on our infrastructure. So the goal here is to have the first workflow with RANS simulation to screen all the wind direction and atmospheric stability. Here it's a preliminary computation for only 4 wind directions with a neutral atmospheric stability and a fixed inflow speed of 10 meters per second. So the simulation time is 10 minutes for this one, and the area is 100 kilometers squares with at the maximum level of mesh refinement, we have cells of 12 meters by 12 meters by 3 meters. And the total is about 350 million cells. This one, interestingly, was run first on the Kestrel cluster on GPU by Harish Gopalan. It does not mean that there is higher performance for this kind of physics-based simulation software on GPU. It just means that GPU are more recent on the Kestrel cluster, and the Slurm queue is less loaded, so it's easier to run computation. So it doesn't presume the performances of GPU over CPU. And it's about 2 to 3 hours per direction for each computation. And so we generate maps of wind deficits. So here you see for this 10 meters per second inflow, the wind deficits plus minus 5 meters per second in the scale. Here, the map is generated at it was also post-processing specifically generated for us. A map at 8 meters, 8 above the ground. And here you can see effect of acceleration of the wind speed, coastal effects that are very interesting for our business. And also you see the acceleration above the ridge on one side of the ridge and deceleration of the others. But what is the most interesting map for our business is the map at 100 meters height, because 100 meters height for this sector, this is the height of the hub of the wind turbine. So this is where the inflow is important for the energy production. And you can see only with those 4 directions for only one wind speed and neutral atmospheric conditions that there is a lot of discrepancies in the area according to the wind speed. And from that, we extract wind speed deficit for the location of the turbines. And we add additional information to the engineering model to enhance the accuracy of the annual yield predictions. Here in this last table, I just present some computing times that we had during the development phase of the WFIP2 canyon for a reduced area of 25 kilometers square and also for an enhanced area of 50 kilometers square, both for runs on LES simulation, on CPU and GPU. So you see that performance are interesting on both sides. For us, it's interesting also to have a possibility to run on GPU, even if our first target is CPU, purely HPC infrastructure. But in the future, if we are forced to have pure GPU systems, we are able to run those simulation also. It's important to think for the future. And what is more interesting is what we plan, a type of simulation we plan for the future for this project. Oh, sorry. For these projects. So we have screened different project size, simulation size that can be done during this project according to the size of the wind farm we want to simulate, the type of simulation runs with all the sector, very precise or not, so we want different wind speed, atmospheric stability or not, or LES simulation or meso-micro coupling. So the smallest simulations we want to do for those workflows are with 256 cores for about 8 hours per simulation, and about 50 simulation for one site, for one study. And we can increase that up to 1,000 cores with 360 simulation runs for a study, decreasing the the time of the computation because we have more core and there is the scalability of the software. We have also different kind of simulation we want to perform. For example, with 2,000 cores and 72 hours, 3 days of simulations for LES simulation with a smaller number of runs per study. And we can go up to more than 3,000 cores on 2 days of simulations for meso-micro coupling. I don't speak here about the very shiny computations that we want to do in the future, perhaps on the European exascale computer or thing. This is not for our own infrastructure. So it's time to conclude. So the main message here is at Total Energies, we are investing a lot in high fidelity simulations that is running on high performance computer, on our own high performance computer. There is need now and for the future. And in fact, the resource needs are increasing for this domain, the wind energy in the company. To do that, we can't do that alone. So we have this opportunity to partnership with the National Renewable Energy Laboratory and to use all those open source software, high quality software that are developed for current and future infrastructure. So thanks to this academic partnership. And after 1 year, it is a success. We were able to deploy all the software stack and run the first simulation. But you have to know this is a large effort. This is not straightforward to just take research software and put it on our HPC infrastructure and just click on the button. No, there is a lot of people involved, more than 10 researchers and people on the NREL side, and tens of people with different teams in Total Energies, including cybersecurity and other people. So it's quite difficult. And now it's well adopted by the R&D, so really a success. And for the next year, we plan to enhance the models, have better models, faster, use heavily this stack in R&D project, and also have a go or no go, and it's always not decided, for real industrializations of the projects. But for that, we need really long-term support of the stack, of the full stack, to use it as a official tool for industrial study inside the company. And sure, this is not a replacement of commercial tools. It is a complement that adds a lot for our research. Thank you very much. If you have questions.
Thank you.